Okay.
Manandra, we shall start, is it?
Yeah, good evening all.
Let me
Please unshare the screen.
right. Okay, now
Good evening all. So sorry for a small delay because there was a technical snag. I request Dr. P.S. Babu, the Vice President of Breakthrough Science Society, Kerala, to preside over the meeting.
Okay, good evening, everybody. All are eagerly waiting for the presentation of Professor Amber Habib. I know that the executive committee members of Breakthrough Science Society, including General Secretary Saumitrada, and probably the members of the Presidium, and most importantly, the maths teaching community, many of them will be here. So the maths curriculum has been pushed without proper consultation with the subject experts, and it is causing an anxiety and worry among the teaching community all over the country. So we want to know the good and bad of this, where it is going, waiting for an expert presentation on this. So I request Professor Amber Habib to start the talk and presentation.
Just give a brief introduction of Professor Amber Habib. Professor Amber Habib is a professor at the Shiv Nadar University, Delhi. Yes, also taught at St. Stephen's College, University of Delhi, and held postdoctoral positions at the Mehta Research Institute and Indian Statistical Institute. Professor Habib did his MS in mathematics from IIT Kanpur and PhD from University of California, Berkeley. His research interests are in line theory, representation theory, and mathematical finance. For many years, he has been interested in how mathematics education at the school level and college level can be made more interesting and fulfilling through special topics, projects, and appreciation of the myriad links of mathematics with other disciplines. He has contributed to the curricula and activities of several universities, as well as national bodies like NCERT, and regularly teaches in the workshops and camps organized by mathematical training and talent search programs. He has authored or co-authored 4 books on school and undergraduate mathematics. So welcome, Professor Habib.
Okay, thank you so much for the invitation, to be here and to talk with everyone and to share some things about what's been happening in recent months with undergraduate education in India. So let me start sharing my screen. I'll start sharing my presentation. Okay, so I hope that it's visible now.
Yes, Professor.
Okay, so it's been very interesting. These are some newspaper headlines from around September, October of 2025. And it's unusual for mathematics to be in the headlines in this way. But what had happened was that around August, the University Grants Commission had released the draft curricula for various degree programs, so various disciplines, about 9 or 10, not just maths, but chemistry, geography, and several others. And very quickly, there was a lot of concern in the mathematics teaching community about the content of this curriculum and several aspects of it. Today, I want to sort of set it in some context that what had been some of the trends in college maths education in India, and also, what had been seen in the world. Where have people been trying to go with maths education in colleges and universities? And by contrast, what this curriculum is taking us to. Okay. In fact, the very first headline here is that Kerala rejects UGC's draft curriculum network. And there are many others. There are several opinion pieces. One of them is by me in Times of India, UGC, please do the math. Uh, there was an editorial in Hindustan Times saying that this curriculum is not on and the government should listen to mathematicians. There was a petition by the mathematics community, which quickly attracted 900 plus signatures. And in fact, many more signatures from citizens, but these were the signatures from professional mathematicians, researchers, and teachers that were, finally submitted by us to the government. That please take these concerns on board. And in October, there was a single article saying that an expert panel has been created to review the UGC draft curriculum due to all the concerns that people have expressed. Unfortunately, we are still waiting to learn more about that panel and what it may be thinking. Okay. Now, let's start the story about 25 years back. And this is a personal reason. Of course, the story goes back much further. But this is around the time that I first, started teaching in a college. I had finished my PhD in 1997, done a few years of postdocs, and in 2001 I had actually started teaching. And that is when the UGC had released a model curriculum at that time. And the quote I've given here is their expression of the general aims of the curriculum for all disciplines. So what we are seeing here is the overall approach and not just for mathematics. But there are many interesting terms and phrases here which have relevance to what happened later. Okay, so one is that they say that the curriculum needs to come on board with whatever are the recent developments in the subject and should introduce innovative concepts. And it should allow a flexible cafeteria-like approach, and also that new papers should be introduced to cater to what's happening at the frontiers in the subject. This flexible cafeteria-like approach was supposed to be one key departure from earlier programs which have a certain fixed structure. And here, the student is supposed to be able to sample as they wish from various offerings. Okay? And one of the concerns that many of us had right away is that the cafeteria is kind of a commercial entity, and you don't just have flexibility to take what you want. You can take what you want, provided that you can pay for this flexibility. And so this appeared like it might be the gateway to not offering the same education to everybody, but allowing it to be differentiated by what people could afford to buy from the cafeteria. Then this is, what the mathematics committee had come up with, their general descriptions of what they were aiming for. They wanted to increase multidisciplinary skills. They wanted to link the general studies with professional courses and introduce bridge courses, which would allow, for instance, students from other disciplines to learn some transitionary mathematics to allow them to take more serious courses and so on, allowing, as they say, both vertical and horizontal mobility. Okay. And there was a bit of discussion of what is it that mathematics education, should convey in terms of mathematics itself. So it should convey a thorough knowledge of fundamental principles, methods, results, and the power of mathematical ideas, and how to use them in applications through all the phases of modeling, solving, and interpreting. And this committee had members from various state and central universities, and as well as research institutes. I have listed, the places that people were from. So at least this was a committee with a good representation, from people from different backgrounds, catering to different audiences, and therefore increasing the probability of a national curriculum that really would cater to the needs of a diverse country like ours. Yeah. But let's take a quick look, at what was there in this 3-year program that the UGC had proposed in 2001. In the first year, you had calculus and differential equations, and then matrices, linear systems, a bit of classical algebra, polynomials, and permutation groups. Here too, as you can see, is real analysis, differential equations, more calculus, statics and dynamics. And then third year takes you to more abstract mathematics, more of real analysis, metric spaces, Silo theorems, But also it takes you to a bit of programming and probability. Yeah. And looking at this, you can see that it has quite a diverse amount of mathematics here, a large and diverse amount. Nevertheless, nothing is perfect. And for instance, you see a big gap that the second year is basically all analysis and has nothing of algebra. And again, the applications are coming in very late and therefore are very restricted. You have probability, but you don't have statistics. Right? And so in terms of what a modern undergraduate curriculum can be, this certainly was not perfect. It had some lacks. And now I'll jump a few years to 2015, and what I'm showing you now is part of a document from the United States, from the Mathematical Association of America, that provided a link at the top. They had a committee to look at what undergraduate mathematics offerings could be like in modern times, what it should take care of. And they addressed it at two levels. One, they said, what should be the mathematical content, but also philosophically, what is it that the program should attempt to equip students to do, right? And so, for instance, you see here, they are talking of what should happen beyond the curriculum, that one should start to view mathematics as a liberal art. One should prepare students for graduate studies. We should pay attention to assessment, to the use of technology, and also undergraduate students could be introduced to research. So these are other more general aims that an undergraduate program could have, apart from the bare descriptions of the content and the topics to be addressed in the undergraduate program. Okay. Now, apart from these sort of overall goals, they did also convey, think about what should be there as the content in terms of topics. And certainly it's, the standard thing should be there. You should have concepts and methods from calculus and linear algebra. There has been a trend over the last couple of decades to recognize that linear algebra is really important in today's world, and basically it should be placed on an equal footing with calculus due to its many applications, to the worlds of data science, machine learning, and so on. Then students majoring in the mathematical sciences should acquire other skills related to it. They should learn to read, to understand, to analyze. And as they proceed through the program, they should be able to produce proofs of increasing depth. So the course offerings and how we teach them, needs to be carefully graded so that the student grows as the program goes along. The program should, of course, address modern applications and areas such as data analysis, computing, and modeling. And then you should be able to cover key ideas and concepts from a variety of perspectives to see that there are different ways of looking at mathematics and to appreciate the breadth of mathematics. We shouldn't just stay confined to the world of mathematics. We should see how it interacts with other disciplines. And in particular, we should be exposed to how other disciplines view mathematics and attempt to make use of it. And then within mathematics, each of us as a mathematician has their own way of looking at mathematics. Some of us prefer analysis, some prefer algebra. There's the continuous way of thinking, the discrete way of thinking, and we must make sure that our students are exposed to all of these different perspectives that mathematicians have of mathematics, right? And they get the full experience of doing mathematics. Okay. And so far it's been about breadth, and therefore we must make sure that you don't just end up with a lot of knowledge of different types. You must also learn in depth, and at least one content area therefore should really be gone into depth by each student. And then you should not just have, doing assignments and quizzes and exams, but you should have some sustained study of a mathematical topic through what you really need to become successful, whether as a mathematician, academically, or in a career where you apply mathematics, where you would have a sustained project or working on something, and you should be exposed during your undergraduate studies to this kind of activity as well. And this is basic. Of course, the students must learn what are possible careers after mathematics. So here are some 9 sort of points. They had others, but I've just selected 9. Basically, to convey that when we are deciding what a mathematics curriculum is, it's not just about saying, do I include this particular topic or not? There are many aspects to think about so that we are portraying a proper picture of mathematics to the student and opening up all the different possibilities and potentialities to them. Yeah. And so when a modern curriculum is being created, one hopes in that curriculum to see a discussion of points like these, and one hopes in the syllabi and so on that it will show that the committee and the people creating the syllabi had time to think about such things and had done their best to incorporate as much as they could into the curriculum itself. Now, at the same time as this document was being produced by the MAA, the UGC in India was bringing out a new curriculum, okay, in 2015. And it starts with a very interesting statement about the situation before 2015. It says that majority of Indian higher education institutions have been following a system which obstructs the flexibility for students to study subjects and courses of their choice and their mobility to different institutions. And in fact, the new curriculum had nothing good to say about anything that had come before. And this was the major criticism. They said that students do not have the choice to study the things that they like or to mix and match different things. And they cannot move easily from one institution to the other. And this is not in the sense that you do a bachelor in one institution and you do a master's in another. What they're talking about is if you're doing a bachelor's and after 2 years you're not happy in a certain place, can you move to a place which has a different kind of bachelor's or different students, different teachers, and could you then just transfer to another place and be happy over there? So they wanted to increase mobility of this type. Okay, so these are the important things that they have highlighted in judging what was the state of education before. And again, this is for all disciplines, not just for maths. And here are things that they wanted to do. They said that we must shift from teacher-centric to student-centric education. And as far as I can figure out, what they meant was the teacher-centric, they mean that one is concentrating on the content. So it's about what the teacher says, and that is what the student has to do. And student-centric means that one is thinking not about content, but one is thinking about the effect on the student. One is asking what is it that the student is learning from this and what is it that the student is able to do after the program. And they claim that before them, people were only teacher-centric, whereas they were going to make everything student-centric. This relates to their criticism. They want flexibility for students to study at different times and at different institutions to complete a degree. And all sorts of papers should now be incorporated in the degree, interdisciplinary, intradisciplinary, skill-oriented. And so for this, they created all sorts of categories of courses: core, discipline elective, general elective, skill enhancement, ability enhancement. Okay. And so let's take a look at what happened due to their desire to have such a curriculum. Okay. So this was called the choice-based credit system, CBCS, and for mathematics. Okay, so there are some rearrangements of the old curriculum. Maybe an improvement is that algebraic thinking happens more evenly through years, and analysis is evenly distributed as well. But there are very interesting omissions. In fact, if you see for a curriculum which is trying to promote interdisciplinary thinking, and therefore we should promote the connections of mathematics with other disciplines, and at the very least should promote the applied areas of mathematics, that has in fact been reduced in at least the core part of the curriculum. In all this, there was just a single course on numerical methods, and there was no probability, no statistics. Okay, and the ODE, PD are not really, what you would use, not modeling courses. They're just, if you are faced with such an ODE, then here is the technique for solving it. So in spite of all the big talk, in the introductions to these curricula, the actual reality that one faced was quite different, right? So in fact, no dedicated programming course, an omission compared to the earlier curriculum. So after 15 years, one is in fact backtracking on the most important things that you would think about. Are we making our students fit for modern data science? Or by then machine learning had certainly started coming up in terms of undergraduate education. And there is nothing of that type in the 2015 syllabus, right? No probability statistics at all is, in my opinion, just a shocking omission for a modern undergraduate program in mathematics. Okay, but be that as it may, this is still 2015. We have to ask, and what about 2025? Okay, so now we have something called an LOCF, right? A learning objective-based curriculum framework. And so what are the promises that are being made to us now, and how do they differ from both promise and reality of earlier times? Okay. So now we are informed that the new curriculum, and again, this is for all disciplines, this curriculum reflects a forward-thinking approach. It offers, well, this is for mathematics, but the things said here are said, more or less for every discipline. So this curriculum reflects a forward-thinking approach, offering students a robust foundation in mathematical concepts and skills, emphasizing value-based education, interdisciplinary relevance, and integration with the Indian knowledge system. So in terms of promises, if you look at earlier curricula, what is new is the integration with the Indian knowledge system. And maybe a little more emphasis on this value-based education. But otherwise, it is the old promises, but with an increased emphasis on values, whatever they are, and integration with Indian knowledge system. And these, when we look at the 2025 draft curriculum, then it will be important to keep these things in mind, right? And I think we will come back and test it against what is being said over here. They're claiming that they have actually produced a well-structured set of core courses and with complemented by wide selection of various other kinds of courses. And therefore, again, we should test when we do look at the curriculum in a few minutes, are the core courses well-structured? Is there actually a useful wide selection of other kinds of courses? What is really there in the general electives and the discipline elective courses? Okay. And then there is the issue of the learning objectives, which are the other innovation that they claim is being introduced in the new curricula. Right? And this is related to what in 2015 was called the shift from teacher-centric, so-called teacher-centric, to so-called student-centric education. That each course would have clearly defined objectives and learning outcomes. Now, what is a learning outcome? A learning outcome for a course or program is an ability that the student acquires due to that course or program. Okay? And how do you know that the student has acquired such an ability? So it should be an ability that you can test. Okay. And so the assessment for your course should be such that you can discover whether the student has actually acquired the learning outcome that was promised. And so through this, there is supposed to be that the student will have a better idea of what they're in for, what they are going to gain, and they can make more well-informed choices. And they can experience what the committee is calling a goal-oriented academic experience. Okay. I personally, when I read something like this, there are many things, they say, okay, is this what a university education is supposed to do, or is this what a mathematics education is supposed to do? What is education? So, you're trying to equip the student for the world, but not just skills, right? A higher education, a college education is not a job training program. You should learn things which are useful when you head out into the real world, but it is meant, or it should be meant, to do much more than that for you. You should learn how to think about the world you are in, and critically. And you should be able to think not just about, okay, I will apply this mathematical formula or algorithm. You should really be able to think, is this problem I'm thinking about quantifiable? What is the ways in which I can quantify? Is that meaningful? All this sort of thinking, the critical thinking skills you need to acquire, these are also parts of an education. And therefore, education has a very strong component of experimenting. When you offer a student choice, right, what is the point of it? So the point of offering a student choice is that you are allowed to experiment, and some of those experiments will be successful and some of them will not be successful, but through them you will figure out what is it that you want to do with your life. And this is not quite the same thing as saying that I will give the student a goal-oriented academic experience. A goal-oriented academic experience is a much narrower target to have, right? And that is appropriate, I think, for a technical program, but it is not really appropriate for a general undergraduate program, and certainly not with the kind of promises that have otherwise been made to the students. So in my opinion, there is a lot of contradiction within the statements that are being made within the documents of this program. So first, now let me come to the LOCF, and let's do a very quick comparison with the previous 3-year program. And now remember that the LOCF has become a 4-year program. And while you can exit after 3 and take a degree after 3, all, the NEP and all related documents are very clear that the desirable thing is 4 years. And 3 years is just if for some reason you are not able to do 4 years, you didn't have the money to do 4 years, or somehow your grades were not good enough for you to deserve 4 years. So it is, a 3-year degree would not carry the same value as a 4-year degree. Right? So this is the ideal that they have, that now everyone, if possible, should do a 4-year program. Now, if I compare this with what was happening in the 3-year program, it's very interesting. If you look at the core part, the 3-year program had 14 core courses, so does this, but the credits have shrunk. Credits have shrunk means that the teaching time has shrunk to 2/3 of what it used to be. So overall, even though you are there for 4 years, but your core is getting only 2/3 the time that it used to get earlier. This is partly compensated by the discipline subject and specific electives, which are 6 instead of 4, and partly compensated by the project, which is 12 credits. But it is at best compensated. You cannot say that a student coming out of a 4-year LOCF program will know more mathematics than the student coming out of the 3-year CBCS program. Okay, and in fact, I think that the student is most likely to come out knowing less in this 4-year program than they did in the 3-year program. They would know more about other things. They would know something about a minor, and they might have done more of, so many of these sec and VAC courses and some internships. So they may learn more about other things. But unfortunately, what they will learn about other things on the whole will be very shallow, because all these sec, VAC courses and so on are courses that are meant to be accessible to every possible student, and therefore none of them can really be a course that goes into depth or that really lets you build up an advanced skill. They all by default have to be shallow. But anyway, this is what one can see just by looking at the credits and the teaching hours. But let's look at the actual content, where I think many more alarming things await us. Okay. All right, this is the 4-year that the UGC has prepared for us, right? And I'm showing you the sort of program, right? All the core courses I have named in this table. And you can see that the first 2 years, there are only core courses. And then in the 3rd year, there are 2 elective courses in mathematics. And the 4th year has several elective courses, 6 elective courses in mathematics. Okay. And again, the core part starts off okay, there's calculus. But remember, this is a whole year. In a whole year, you have learned calculus, multivariable calculus, some analytical geometry, some matrices and linear algebra. Okay, so, and one thing that's already missing, the CBCS that I had shown you earlier, if you look at year 1, there is a course on what you might call foundations, which is, the basics of mathematical language, sets, functions, and so forth, as well as techniques of proof, So what is mathematical thinking? There was actually a component of that in the year 1 of the CBCS. That actually has been very important. I think over the past 20 years, there's been a strong realization that you can't just start teaching mathematics at university to students because the expectations at university are very different from what they are at school. Suddenly, you want them in school, they have learned how to compute, how to apply formulas. And in university, you suddenly want them to prove, to apply reasoning, to be very clear in their communication, to be flexible in their communication. And this needs training. You can't just start a course and say, well, now I suddenly have these expectations. You actually need a course where these expectations are taught to the students and they are taught how to navigate their way through this. And so, for instance, it was mentioned that I teach in the mathematical training and talent search program. And this is while our whole program is based on, conveying mathematical thinking to students, I think 20 years ago, it became clear that you in fact need a separate module for it, right? And so when students come to us after 1 or 2 years of undergraduate for the summer camp, we have a whole unit of what is mathematical thinking, what is communication, what is rigor, what are proofs, right? So they have to be equipped for it. The world over, such courses have been coming into being. Very nice books have been written, very nice courses have been floated. And in 2015, we had also made a start in that direction. Into 2025, suddenly vanishes. Right? There is a backward step. Now all those things, this bridge portion, which is so important, especially given what has happened during COVID and after to students, where the high school courses have been cut. And while it is understandable why they were cut, but the cuts are very significant in terms of their preparation for a university education. And they're coming in now, not knowing, knowing much less than they used to about many things like sets and functions and what is a proof. At least that is what I find in my classes, that things I could take for granted, say 7, 8 years ago, I cannot take for granted anymore. And my university has also adapted to it by introducing bridge courses in the first year to help students through this. but the UGC has actually gone the other way. Okay. Another interesting thing are these courses called Analytical Geometry and Theory of Equations. These courses used to be there 20 years ago and then gradually were abandoned because people thought, let us use the time to teach more modern topics, or let us teach a more modern incarnation of this language, okay, of these topics. And instead, and again, that progress has been abandoned, and one has gone back to the old courses. And you can see, what has happened by looking at the textbooks. The recommended textbooks are books written, like in 1920 or 1910, the really old British textbooks. And so one is going back in time instead of moving forward. Okay? And now, if you have been scanning it yourself while I've been talking, you might notice other interesting things. So one of them I already talked about, the lack of what you would call foundations in the first year. But here is another remarkable thing, that real analysis is completely missing from the first 3 years. Okay, real analysis, which forms the foundation of higher analysis, is totally gone from the first 3 years. If a student actually exits from this program after 3 years, it will be, frankly, horrifying that they would not have encountered real analysis. So there's just one course in one semester, the 7th semester. And so that covers real line sequences and series, limits, continuity, differentiation. It's just one semester. This is a reasonable content for a one semester course, but it is not a reasonable content for an entire curriculum. That, for instance, you have not even made it to integration. So students will graduate from a 4-year program and they won't even know what integration actually is. They will only know integration the way they studied it in school. Okay. Again, there's only one linear algebra course, which is in the 2nd semester, which is a strange mix of topics because it includes abstract things like quotient space and dual space in the 2nd semester, when they have not done any abstract algebra or the foundation sort of things which would even help them figure out what you mean by a quotient space. But doesn't do the practically important things like taking a matrix and finding a basis to make it upper triangular, the really practical, useful things that somebody should do in a first course in linear algebra are missing. And abstract things that they cannot appreciate at that stage are included. Okay. And similarly, algebra is shortchanged. There's just a single algebra course which in one semester tries to do a lot of group theory together with a lot of rings and fields. Okay, a completely unreasonable course for one semester. And if you look at the application side, there's a single course, elementary statistics, which half of it is descriptive statistics and half of it is probability. So again, you would graduate without having a really proper knowledge of probability because you would not teach. We just basically learn the axioms of probability and simple sort of distributions, but not much more. And you do not make it to proper statistics at all. Okay. So the core part in this draft curriculum is kind of massacred because whatever progress had been made from 2001 to 2015, while not perfect, has been abandoned. And we have gone back to older topics, and very basic modern topics have just gone missing from the curriculum. Okay, now, still one could have hoped that because there are lots of discipline electives, so there are a total of 8, one would have hoped that if they have set up a good choice of disciplinary electives, then maybe some of this could be compensated there. Okay? That maybe a student could learn more algebra or more analysis through the discipline elective, though it would be difficult because if real analysis happens in the 7th semester, when are you going to do more advanced course in analysis? The 8th semester already has complex analysis, and how much more can you do? So these are the very unfortunate aspects of this curriculum, but even more unfortunately, the story doesn't stop here. Here I've shown you a table of all the disciplinary electives that they have mentioned in their curriculum. The column on the left is all the sort of programming sort of related ones. So there are multiple courses teaching you programming in different languages, C, Fortran 90, Python, C++. 4 courses which just teach you programming in some language or the other. Which is actually not very much variety. You don't need to learn 4 different programming languages. You learn one maybe, and then you just pick up the others. And so the actual applications of all this programming are not so many. There's a course on mathematical modeling and simulation, numerical methods. There's a course called Mathematics for Machine Learning. But if you think from the title that you will learn machine learning in this course, you would be mistaken. This is actually the basic mathematics that you need for machine learning. So, funnily enough, this course, the disciplinary elective called Mathematics for Machine Learning, is finally the course which tells you what are sets and functions and what are bijections, what are relations, and so forth. Okay. And it tells you very basic things about linear algebra, which should have happened in the core course. They happen here. And the machine learning part is just some terms and definitions. The recommended books are just a list or lists of terms from machine learning. They don't actually conceptually teach machine learning. The courses in artificial intelligence, I wasn't equipped to understand whether that's a good course or not. And then optimization techniques in machine learning. On the other side are all the others, right? And again, you see that it's a very unsatisfying mix. Optimizations, integral transforms, I mean, they are fine. Calculation of variations, I don't object to any one of them as such, but certainly, what is missing is very, very important. That metric spaces is something that a student has no option to learn in this curriculum, or metric spaces, topology, geometry, all these modern aspects of mathematics are missing, even from the elective things. There is no follow-up course on statistics or advanced probability. Okay. Uh, okay, so even if a student wanted, to use the electives to become good in applications, they would have difficulty. And certainly, if they want to become good in the purer side in algebra analysis, then they have no option at all. Nobody can come out of this curriculum and be equipped for a master's program or a PhD program with a strong component of modern analysis or algebra. Yeah. And, this is very striking because remember that the NEP says that this 4-year program is supposed to be so good that students can skip a master's and go directly to a PhD if they have a CGPA of 7.5. They would be eligible for direct admission to a PhD. Yet, as we have seen, they would actually come out not being any better at all than students of the earlier 3-year program. And so how they would cope with direct admission to a PhD program, it just boggles the mind. Okay. All right, so that is a lot about what is missing. Let's look at some of what is there, right? And remember that this was one of their promises, that the curriculum would be integrated with Indian knowledge systems. Okay, now unfortunately, mathematics is the discipline which has taken the biggest hit from this desire to integrate with Indian knowledge system, because after all, we do have a very good history of mathematics developed in India. And so that has led to a temptation to include lots and lots of courses related to that. Okay, so while in the disciplinary electives, there are maybe some 18 odd courses of regular mathematics. On the other hand, there are some 12 courses related purely to the history of Indian mathematics. Okay. And so on the one hand, this, If universities offer these courses, then certainly, what you could learn of modern mathematics from the disciplinary electives becomes even less, right? Remember, there are only 8 of them in total. If a student does 3 or 4 of these, of the IKS courses, then real modern mathematics or programming or any other application, they would only have done a total of 3 or 4 courses from there. And so it's not clear what they would be fit for. Now, these courses, I mean, you can just go through the titles. When I started teaching in my current university in 2011, we also had an idea that we want to float some mathematics courses which are accessible to non-mathematicians. And one of the ideas was to create a course in the history of mathematics as a course that would allow you to talk about how mathematical ideas develop, how mathematical principles have evolved in time, and that could happen at a more school mathematics kind of level and therefore be accessible to a wider audience. And I myself have taught such a course several times. So what we are seeing here is something that I'm pretty familiar with. And one thing I know is that while the things are great, but if you start teaching them using modern language and so on, then the course goes actually pretty quickly. It would be very hard to put together more than 2 or 3 courses to cover what has happened in Indian history, in Indian mathematics and history, in a proper way. And they have created 12, which means what is happening here is there's a lot of overlap. Many of these courses repeat what other courses are doing. And for several of them, the ones in the topics I'm familiar with, like geometry and Shulva Sutras, or the Leelavati, or the general courses like development in Indian mathematics, history of Indian mathematics, I have looked at the syllabi and said, okay, how long would it take to teach these topics? And they're supposed to take 60 hours, and I cannot figure out how a normal teaching would take more than 20 or 30 hours for one of these courses. So it's not reasonable at all. I mean, it is just a waste of everybody's time. And then there are some courses which are really shocking, and I refer in particular to this uh, course which is on the top of the second column, which is about developing the Hindu religious calendar, and it talks about what are the principles on what that is based. And it actually, the curriculum says that students will learn how to find the auspicious time for various events to happen. Now, I mean, you can do that as an exploration in Indian history, but there is no mathematical principle at stake. And there is no way that such a course deserves to be part of the mathematics part of a modern mathematics curriculum. Okay. All right. Now I've kind of spoken about my disappointment with the Indian knowledge systems. Now, I don't want to say that history of mathematics does not have a place in a mathematics curriculum. There are certainly useful things to be learned from the study of the history of mathematics. Okay. And I would like to talk a little bit about it. I would like to say that there is a useful and an enlightened way of incorporating history of mathematics into a mathematical curriculum, but this is not it. They have not done that. Okay. And I would again go back to the early 2000s when, and this is the National Focus Group on the Teaching of Mathematics, and they make a comment that talking about lives and mathematicians and stories of how mathematical insights came about can be inspiring for students and can help them connect better to the topic, give a more human angle to what is going on. And again, knowing that mathematics has been an important part of Indian history and culture can help a student feel more connected to the subject, right? And can give them perhaps some confidence about their own self as they take on mathematics. It might reduce the alienation that people sometimes feel when they look at mathematics. Yeah. And when, and so there are different, when you're teaching mathematics, there are different places where, looking at something that happened in history could be useful. For instance, if we recognize that the identification of patterns is central to mathematics, you learn, perhaps start with geometric patterns, numerical patterns, and eventually once you're used to that, then you take on abstract patterns. And there are many people who think that that is what mathematics is all about, right? And you could use what people have looked at historically to come up with interesting examples that you could use in class, okay? And so, for instance, starting with patterns of shapes, students could make a connection with, say, numerical patterns and algebraic patterns, and therefore have a way of moving from geometry to algebra, where algebra becomes rooted in something that they can actually feel. And algebra does not just become, there are some mysterious letters and some mysterious rules for handling them. And, it's just sort of a nonsensical game that you play with rules, which is often what people start thinking about algebra. Okay. And I want to show you, I don't just want to talk about, what is in a curriculum or not. Let's also do some mathematics. Okay. So when mathematicians get together, some actual mathematics should be looked at. Okay. Let's go back, in Indian history, to the Indus Valley civilization, right? And as we know, there were many aspects of that civilization, which speak to an interest in geometry, in geometrical layouts, the use of right angles in the city layouts, and so forth. And also standardized. And one of the important things that is observed is a standardization in the weights that were used, and a fairly uniform standards being used across, you know, uh, a breadth of both space and of time for many centuries, and also over a large geographical area. Okay, so what I'm showing you here are some weights that uh, come that are shown in the National Museum in Delhi, right? And these are made out of a soft stone called chert. So chert cubes, these were found in large numbers right away at Harappa and Mohenjo-daro, then in other places. And people, of course, weighed them and found that the weights are not random. They come, in certain, there's a cluster at a certain weight, and then there's another cluster at another weight, and then another cluster at another weight. And eventually, and so they realized that if you take, say, 13.6 grams as a unit, then the weights that you're finding run in various multiples of this 13.6 grams. Okay. So for instance, if I take 13.6 grams as one unit, then I find bigger weights, which are like 2 units, 4 units, 10, 20, 40, 100, 200, 400, 500, 800. But there are also finer weights, and those go as half unit, 1/4, 1/8, and 1/16. Right? So it's basically, to a large extent binary, but with a mix of base 10, right? So sometimes, because you see that pattern of 1, 2, 4, and then it repeats as 10, 20, 40, and then it repeats as 100, 200, 400. Then it breaks down at the highest weights. But then that's also because, the middle weights 1, 2, 4, 10, 20, 40, these are the most common, the most useful weights, right? By the time you reach 800 units, you are actually talking about a weight that weighs 11 kilograms. Okay. So I think only, maybe one or two have been found of that type, right? So for the higher weights, there's actually very few have been found naturally. There would not have been much use for such a heavy weight. And again, the very fine weights, then where are they found? When do you need a very fine weight? You need a very fine weight when you are dealing with precious things. So when you have precious stones or necklaces, beads, necklaces, jewelry. So it's in the places, in the workshops that were dealing with, with jewelry and beads that you find the very fine weights, right? And that makes sense. Yeah. But the 13.6 grams as a unit, that is something that we have imposed on the weights that we have found. We don't know what weight they thought was a unit, or whether they even thought really in terms of one particular weight being a unit for everything else, right? Often there are different collections of weights in civilization. So you may have one set of weights for one kind of object or one range of weight, and you might have weights of a different name, different unit for other kinds of objects. Okay. So certainly, for instance, in some civilizations, Mesopotamia, the weights used for grains would follow one unit system. The weights used for other things would follow, for liquids, let's say, would follow a different system of weights. So we don't know all that about the Indus Valley because we have not been able to translate the writing, and not much of the writing has been found. But we can play, right? The point here is that we can play with this in a mathematics classroom. You can ask students, what happens if you took a different weight? What if what is called 2 was a weight, was unit? Then something interesting happens, right? Then the sequence becomes 1, 2, 5, 10, 20, 50, 100, right? Look at that again, 2, 4, 10. Everything will get half if the 2 is a unit, and so you will get 1, 2, 5, 10, 20, 50, 100. And that, of course, is a combination we use all the time today, right? Our currency notes work like this. Coins and notes work like this. These are the exact multiples we find today, right? And so you can ask, now this can therefore lead to a discussion of why would different weight patterns or currency patterns be adopted, right? What is convenient about them? How do they make counting, paying, or exchanging more convenient? Right? And so by looking at history and playing with it a bit, you can raise interesting questions that can be addressed in a mathematics classroom, as opposed to just being memorized that these were the weights, right? And then having an exam which says what was the unit weight in in the Indus Valley civilization, and you are supposed to say 13.6 grams. Yeah. Okay. And that shouldn't take much longer. So now, this is something from Mesopotamia. There was a problem which people thought was basically an algebra problem. It took 50 years for people to realize that it actually has a geometric interpretation, and it can be solved through the sequence of diagrams rather than through the algebra which people had assumed below. And this speaks to what the uh, national curriculum framework had said earlier, that there is an intimate connection between geometry and algebra, and studying how areas work, for instance, can lead you uh, to how algebra works and can lead you to formulas in algebra. Okay. Similarly, if we go on and come to the university level, there are lessons that probably are waiting for us in history. For instance, we know that the calculus we teach today has 2 parts, differential and integral. And in school, we teach differential calculus first. And the reason we do that is that many integration problems are made possible if you already know differentiation. So we do it because technically it makes integration easier if you already know differentiation. But in history, there's a huge gap between the two. Integration was basically being implemented by Archimedes in 300 BC to find all the standard surface area and volume formulas that we teach in school today. Okay, and he was basically doing the Riemann integration that we talk about, but in certain examples, not a general theory. Whereas differential calculus only took off really in the 17th century with Fermat and the mathematicians of his generation. That's a 2,000-year gap. That certainly should make us ask, or should make us think that integration intuitively is a much easier thing than differentiation. It took 2,000 years for people to move from one to the other. And therefore, maybe in our teaching also, if we would teach the principles of integration first, we could have a more friendly introduction to what are limits and why we do them. And then we could do differentiation area. is a much more accessible thing than, say, the slope of the tangent line. Okay. Okay, so there is space for history in the modern curriculum, but it is a certain, you have to look at history in a different way, not to memorize, but as a place from which questions arise and suggestions arise for how we can teach today, right? But that is not what is happening here, because what is happening here is not at all, in fact, there is no integration between the mathematics in the core part and the IKS part in the elective part, right? There is no integration. Nothing from one goes into the other. And the history and the IKS part is basically the memorization of facts. If if there were 20 ways to solve a certain problem in 1,000 years ago, then you memorize those 20 ways in that course. Okay, and the syllabus is very explicit about this. It says, learn so many techniques of this, learn so many people's techniques for doing different things. It is not about critical thinking or blending with how we think today at all. Okay, so unfortunately, this draft curriculum, if implemented, will not take us forward. It is not suitable for our present or our future. It takes us back in time, and just I don't have good things to say about it all. So now, what about the future? The title said the future. The future, unfortunately, is up for grabs. If the UGC curriculum really gets implemented or something close to it gets implemented, then the future is rather dark. And by my writings and by my participation in events like today, I'm hoping to, convince people that we need to do something collectively so that the future is not the future that this curriculum envisages, but what a modern curriculum really could be, right? So now there is machine learning, there is AI, there are all sorts of applications. There are ways, and it's happening all over the world, to teach the relevant parts of mathematics in the undergraduate curriculum, to teach in such a way that students can more easily bridge to the modern applications. And we should not be giving up on that. We should be trying to figure out how to do it for our students. And we have to fight so that we can do it. Okay. So I think I should stop here. I'm sorry, we started late and I have gone beyond the time. But if somebody wants to ask me something or raise some topics, certainly we should take that forward.
Thank you. Professor Habib. We actually got quite a few questions on the chat box.
Okay.
And I'll call upon the person who posted the question one by one, and I will actually first call Mr. Aman Singh. Mr. Aman Singh, you have placed quite a few questions. Maybe you can just tell directly to the speaker. Are you there, Mr. Aman Singh? If not, maybe I read.
Yeah, you can read. That will be fine.
Okay. Okay. So his first question is, maybe I club the two questions he placed at the very beginning. On what academic basis are non-standard topics included as core modern content? This is the first question. Second, what will be the long-term impact on India's research ecosystem if undergraduate mathematical maturity declines?
Yeah, I mean, I think, hello, Aman. I do know an Aman Singh from MPTS. Not sure if you are him, but in any case, on what basis something we can't say because they have not bothered. This curriculum does not come with any sort of introduction that truly explains the philosophy. The introduction to this curriculum simply says that this is a great curriculum. It does many things, but it does not go into, why we did certain things, or look, we have included this course and students will be benefited in this way. So the curriculum itself does not do it. And when the curriculum was criticized, then that certainly opened uh, a space for the committee to respond and to say, look, this is why we did it. But they have chosen not to do so. Only the UGC chief has spoken out and has only again said it's great and nothing needs, that people are unnecessarily worried. Okay. So unfortunately for the first, because it's, what was the committee thinking? I can't tell you. But the second, if this happens, then I mean, it's bad news, clearly bad news for everybody. If undergraduates come out of a 4-year program, not knowing analysis, not knowing algebra, not knowing much about linear algebra, where is this going to get fixed? Right? Now, remember that once you have a 4-year undergraduate program, after that, the master's, even if you go for a master's, is supposed to shrink to 1 year. So I mean, that's just, whatever problems are caused here will then be magnified by the fact that the masters cannot fix it, because the masters is not even the previous 2 years, it's a 1 year. So in fact, there's an even bigger loss waiting at that stage, right? And when these students come to PhD, what happens? So, and I think PhDs are definitely going to suffer. They will have to increase their coursework. So people will not be able to start research as early as they could. The first couple of years will perhaps be needed for coursework to remedy, what has been done to the students before that. Yeah, so it's not good for the research ecosystem at all. Whether, often it happens that a curriculum is at least good for pure, or if it's not good for pure, at least it's good for applied, at least somebody is happy. In this one, I don't think anyone can be happy. Both pure and applied have been splashed, which is a remarkable thing to achieve. Yeah. And they've done it by just putting in lots of obsolete mathematics, which is not of use to either pure or applied to them.
So, Professor Habib, just to add to this as a question, see, obviously, if you want to pursue research in mathematics, this is one question. But other than that, mathematics being language for all science or science disciplines, I think it's probably have a domino effect on the other fields. Can you say also on that?
Yeah, so actually I didn't, include it in these slides, but part of the curriculum, of course, is also to create mathematics courses for other people, right? So I have only talked to you today about what is the maths curriculum for people doing, say, a BSc, honors equivalent in mathematics. Okay, now, but what if someone is doing physics or economics or something else and they want, whatever, they will have some maths compulsory, but what if they want to learn more? Then again, those offerings are very sparse. There are courses like mathematics for physics, mathematics for music, mathematics for languages. I think there's a course, philosophy of Indian mathematics. There's a course called mathematics and meditation. Okay, so these are the courses like this are the courses that are being offered to other disciplines. And as you can guess from the names, again, I mean, actually, it's very, and all of them, are very funny, self-contradictory courses. You're teaching a course to a non-mathematician, and the course is titled Mathematics and Music, right? And the course says that if you have 10th class mathematics, you can do this. It's a very general course. And then the course includes in it Fourier analysis and applications of Fourier analysis. Now, of course, that's important in digital music and digital processing, certainly, practically, yes. But given your audience and the maths that they know, it's completely impractical. Right? And so again, it's thoughtless. And if you are a non-mathematician, or if you're in some other discipline and you're hoping, to take part in the mathematization that is going on of various disciplines, the increased use of mathematics in various disciplines, Then, unfortunately, the courses that have been included in this curriculum for that purpose do not end up serving that purpose.
Thank you, Professor Habib. Now I will move to Mr. P.R. Vignes. If you are on the audience, can you please place your question directly?
Yes, am I audible, sir?
Yes, please go ahead.
So thank you, Professor Habib, for your talk. So my questions are quite self-explanatory. I'll just read the questions from the chat that I posted.
Sure.
So is the curriculum framework that the UGC have drafted, is it kind of a draft curriculum, or is it the final version that they are giving it to us? And
Yeah, I
one
mean,
more, if I can ask.
right, perfect. So they released it saying it's a draft curriculum. I think the citizens of the country were given maybe 3 weeks in which to submit feedback about the draft curriculum. Okay. And that is why, as soon as we started realizing what is actually in the curriculum and people started seeing what's there. In fact, maybe this also answers the earlier question, what I would say now, that it's very interesting, like who was upset? Everybody was upset. College teachers were upset, university teachers teaching masters were upset, research institute people were upset. Everyone saw some will be affected immediately and others will be affected down the line, but there's nothing good in it for anyone. Okay.
So
Now,
is
in
it
terms of,
binding?
is it draft or final? Well, they said it's draft. They said give us feedback. So people have submitted feedback. People have submitted individually. People have submitted petitions. The Mathematics Teachers Association of India has submitted, for instance, the official feedback from the viewpoint of the whole society, saying what it is that they don't like about the curriculum. Now they have acquired a lot of feedback. Now, whether that draft curriculum will be final or not, I mean, one has to be inside the committees to know, okay, are they actually willing to make any changes in the draft curriculum? But the first reaction from the UGC chief or the ministers was not encouraging. Okay. They said that these objections are because people have not understood the curriculum or people are motivated. The curriculum itself is a very good curriculum and does not need significant change. There was a news item in October that a review committee has been set up. I had shown a link, that was in my first slide. But I think that was said to make some of us feel better that something is being done, because actually after that, no more has been heard about that review. Nobody knows who's on the committee, what they are doing.
Like one person had asked whether it is binding or not. I feel it is just a model curriculum, right? So the universities can model it around it. So can they
So
have
far,
some
they have not
deviations?
said anything like that. Okay. So now remember that 2001, it was used to be called a model curriculum. And it explicitly said that this is a sample that universities can use. 2015, they dropped that. They said everybody has to do this. Then when people objected, they said, okay, you can change by 20%, 30%. And people use that flexibility to modify to some extent. This curriculum so far has, in the written document, nowhere does it say that universities will have flexibility. Maybe the final will give way because of the complaints and give some flexibility. But the draft curriculum itself had no sentence to the effect that universities would have flexibility in implementing this curriculum.
Thank you, Professor Habib. Maybe before I jump to the next question, I would like to have also a couple of questions. I will place them together so that you can answer them collectively. So far,
And sorry, just one sentence to add on. You see, even if we get some flexibility, but we should have a good base on which to build the flexibility to fine tune to our own students, circumstances, goals, right? The base should not be a bad base. Should have a good base. I mean, so saying that there could be flexibility does not excuse, a bad curriculum to begin with. Why should everyone have to fix it? It should be a decent curriculum to begin with, and then we should have flexibility to improve it and make it even better for our varying circumstances.
Thank you, Professor Habib. So the next question, I will place them place them together. So the first one is, what may be the motivation for UGC to introduce such a change? This is first. Second, how Indian knowledge system or Vedic mathematics really help the math education? This may be a redundant question, but you can still club them. And there were several mathematicians involved in drafting or proposing this change. So didn't they see what impacts it may bring, or they were compromised? And fourth, is the core part reduced essentially due to accommodating this Indian knowledge system part?
Okay. What were the people in the committee doing? I mean, I can't say. I don't know them. But, I said something at the start for a reason. I said 2001 committee. The committee was well described. It had the names and it gave their affiliations. So you knew exactly who had done this. It was possible to reach out to them. If you were unhappy, you could reach out to the individuals and discuss. 2015 curriculum did not mention the committee names at all. And so that was one of the unhappinesses at the time, that why is something so important to the country being done, in secret? Why do we not know who is responsible for it? This time it's a little bit better. I mean, they shared the names. They said, we thank A, B, C, D, E. Curiously enough, they did not give their institutional affiliations. Okay. Which is a strange thing to do, but I leave it to you. The draft curriculum is out there. Those names are out there. You can Google them and you can find out where they are from. But as far as I could go, I could, if there were 5 people, I could find out where 3 were from. 2, I could not find out for sure where they are from. There was not much available about those particular names. Okay. So, and this is also then our concern about this review committee which may have been formed. Who is on it? You're doing something for the country. I mean, shouldn't you show who you are, and we can appreciate that you are doing something for the country. But for some reason, this information is not shared nowadays. Okay. Yeah, so we don't really know for sure who the people are, and some you can suspect who they are, some you know who they are, and I leave that to you to look at it, and then I think it will be fairly obvious why we are seeing such a curriculum.
Thank you, Professor Habib. We actually received several more questions, but we won't have time to really take all of them. So maybe one last or two last questions we can consider. One coming from Dr. Anupam Ghosh. So Dr. Anupam Ghosh, if you still on the audience, can you please place the question directly?
So please, you can proceed, please.
Okay. So the question is, what would the optimum curriculum framework be in nutshell? So this is the question.
You see, actually, one of the disappointing things is not that good mathematical curricula are not available in India. Okay, there are many places with, when I started looking into this one, and of course I sort of went to look at others, and what you have currently is you have places like the IITs, and they have their own curricula for their students, and you have the Indian Institute of Science Education Research. They have their curricula for their students. And there are many autonomous colleges. I saw some in Calcutta University. I saw some in Bombay, which had used the 20 to 30% flexibility that the previous one had to create what I felt were very nice, sensible curricula for their students that were taking into account the background of the students, that had good books in them, accessible goods. The teachers or whoever created the syllabus had done good homework, and so we have a variety of good curricula in the country. Okay. And there are two things. There is a variety, which is very important. You should have a variety. Every institution has a different goal, has a different kind of student coming in, different kind of ambitions for what those students should be able to do at the end. Different languages, all sorts of things are there. And we should have diverse curricula. Why should we just have one? Okay. And these people have been doing a good job. Why is UGC not using any of this? Okay.
Thank
So
you.
I don't know. I mean, we have good things in our country, but suddenly we just declare that they're all useless, and then we put something in place that is not as good.
Yes, thank you very much, Professor Habib. Now I will just call upon Professor Prosenjit. You also placed a few questions, but I will request you to concise your questions so that we can also finish the program on time. Professor Prosenjit.
Hello.
Yes, please.
Yeah, one question already Professor Habib has answered. So the other question I placed is what is the difference between this multivariate calculus seen in first year and the vector calculus seen in second year in the recent syllabus you have shown? So it is not clear.
Yeah, I mean, there's a lot of commonality, but I think basically it's something like the multivariate calculus is more about the differentiation side, and the vector calculus and its side is more about, actual vectors, what is happening with divergence and curl and gradient and the integration formulas that you have for them. So they're not the same course. There is different focus, but there is also a lot of commonality between them. So it is a little strange. Okay, why has it been done like that? Did the people creating these syllabi not talk to each other? Okay, oh, you are doing this and I'm doing that. Okay, let me. So this certain lack of coordination. And I think that you can see over the entire curriculum. There is a lack of coordination. So one of the right. So like the MA document or points that they share, they say you must have an overall view of what the curriculum is about. What are the overall goals? Somebody or some people need to be really looking at all of it and saying how do things fit together? Where are the overlaps? What depends on what? Is the sequencing okay? And in this curriculum, in my opinion, that is missing to a large extent.
Thank you. There are actually some questions still coming, but unfortunately, we won't be able to take. Just one last question is, let's say, as a mathematician or as any person studying or concerned about education, college education, and higher education, being a student and so, what would be your appeal or your given that there is a serious concern about mathematics education and their impact in a broader academic section, what would be your message? What we should do, you think, or how we can really compensate it, or maybe counter it? What would be your message? And with this, essentially, we'll close the discussion. Thank you very much.
Yeah, that's an important question and a very difficult question. You have to think about it in different ways. What can you do to protect yourself in your own life from such things? Uh, what can you do individually to improve the overall situations? What you can do collectively to improve things? What you can do in the short term, what you can do in the long term. One is struggling with all these different aspects of this. I would say that maybe as mathematicians, we were complacent. Uh, we had seen that funny things were happening in other disciplines, but we thought that mathematics is a universal discipline, it has a universal language for science and so on. And while there may be some playing around with the historical aspects, but overall, we would be safe because we have become so important to all the applications, to AI, to machine learning, that we thought it's automatic that a committee making a new curriculum would create a curriculum that made sense for this. it's needed for the country. Why would someone not? But I mean, we have a mistake, and I think a key mistake is to think, you know, that when something is happening overall to every discipline and to other disciplines and to other institutions, it's a mistake to think that you are somehow special and it would not happen to you. Okay, so we need to, you know, within a college, okay, so when right now, of course, there is a bit of, we don't know what the final curriculum will be like. Will it give us some flexibility? If it does, then make the best use of it as people have done with earlier curricula. But the task will be harder this time because you're starting from the base you're starting from is not as good as it was the last time. Okay. So it will be harder, but that is one thing to do. What can you do for your students? I mean, can I ask teachers that you do more outside the classroom? I would like to ask, but I know that teachers are overburdened, right? People have 16, 18, 20 hours of teaching large classrooms. It is not fair to say to teachers that, the curriculum is not good, but your students need something, do something extra for them. We can, of course, guide them to resources and so forth, but what we can do directly is difficult. And for the students also, things should be solved in the class itself. Why should they have to go to external sources to fix? And therefore, I think, the trying attempt to fix things locally is much harder this time, and therefore somehow the voices have to be raised, and the people who are responsible have to hear from us, and that they have to do a better job. They can't ignore the good things that have been done. They need to take them on board. There are, it's not easy to create. It's not difficult to create a decent maths curriculum. Maybe difficult to create a very good one to make everybody happy. But a fairly reasonable maths curriculum, they already exist. What is so difficult about creating one? Okay. So I think the voices have to be raised and conveyed, and that is not easy, I know, but I don't see how we escape that if we really want something to happen.
Thank you, Professor Habib. So there are more questions. As I mentioned, we won't have time. However, I believe you can directly write this question to Professor Habib, or even pass it to us or send us, and we will pass this question to Professor Habib.
Yeah, we can do that. I can give responses that can be shared. Sure.
Thank you. So with this, the question and answer session closes now. Now I shall call upon Dr. Babu PS for the conclusion, to conclude the program. Yes, please.
Thank you, Professor Habib. It was a detailed exposition of the curriculum and the dangers in it. And we are all thinking of what can be done on this score. And mathematics being a very technical subject, to convey this to non-technical people, the common people, will be our challenge. Let us take up that challenge together. Thank you very much for a good and inspiring talk. Thank you.
I'm grateful that you gave me this opportunity. Yeah, these are important things that are happening, and the more better informed everyone is, the better our future can be. So I think the future of the curriculum lies in that, in things that we all can do.
Professor,
Thank
you
you,
can
sir.
close the YouTube streaming.
Sure.
Thank you very much.